Okay, today is April, what is today? April 8th. Yeah. It should be April 8th, 2025. We will make the closing remarks of mechanical fluids. Very important subject. Of course, we didn't cover everything. As I told you, the Newton law of fluids, for example, which is very important for calculation of gradients of velocities between, let's assume you have a tube here and the water is flowing. The water generates when the fluid is laminar a gradient of velocity of this shape because the velocity is zero on the borders and maximal in the center. But sometimes the fluid is turbulent and this velocity pattern is not obeyed. This kind of physics we didn't do here. And it requires some more specialized courses, of course. But at least we could cover Bernoulli, which is very important. We could cover hydrostatic, very important, buoyant force. We forgot the Pascal principle, which I will mention in a moment. The Pascal principle is the principle of hydraulic forces. You have, for example, you want to take a car, very heavy car here, and you want to apply a small force here. Then you have this area 1, this area 2. And then you apply some force here. Force 1, naturally, there will come a force 2 here, which has to defeat the weight of the car. No? So guess what? It's possible to do it. You have seen that many times when you change the wheels of the car, you use hydraulic forces. When you're going to repair your car, you see how the cars can be put up very easily with hydraulic forces. When the pilots in the plane move the controls, they are moving the wings and so on with hydraulic forces. And the idea of hydraulic forces is that once you input the force here, the pressure, remember that the pressure points in all the directions at each point is transmitted. The same pressure which is transmitted here is the same pressure which arrives here. Of course, you neglect some changes due to the level of the pressure because the pressure which you execute is much larger than those changes. Obviously, there is a fluid here, normally it's oil, some fluid, which transmit that force. Let's define the pressure. How do you define the pressure here at this point? Pressure is force divided area. Then pressure, force 1 divided area 1. And the same pressure is transmitted through the whole fluid and reach this point. So here you have a pressure equal force 1 area 1. But it's equal also to force 2 divided area 2. And then now you have the relation between forces. The relation between forces. Then of course you will see that force 2 divided force 1 is equal to area 2 divided area 1. So the force 2 is much larger, as you can see, much larger than the force 1. And the reason is because the area where the pressure is concentrated is much larger. Then this is called the hydraulic principle operate. It's called Pascal principle. We didn't mention the last time, but I promise you I will mention it. I think I mentioned it quickly, but not in this. I just crossed by, and I focus more in Archimedes and Buoyant force after. Now I promise you that we will calculate the percentage of iceberg sank. I think I derived the formula last time, but in Buoyant force, no? Then this is clear, no? This is clear. The principle is clear. You input some force. There is a pressure at each point of the fluid. The pressure points in all the directions because it's approximately hydrostatic. It's a static fluid approximately because this is very slow process. When you put this force, the fluid moves very slow. It's so slow that you can do the approximation of hydrostatic. That's valid. And of course, there might be more pressure here than here. And the pressure depends on the difference of levels also, because at the same level, for example, at this level and at this level, the pressures are technically same. When the levels are different, there is a difference for the potential energy contribution, no? But that's negligible compared with the external forces you execute when you are pushing. So that's why you don't consider those contributions in this case.
Even at different levels, it would be negligible.
Yeah, exactly. Yeah, exactly. These levels, the difference is not so dramatic, but still, even if there's a difference, the difference will not contribute so much. Of course, if you want to be accurate, you can include that difference also. If the difference is huge, for example, if this car is somewhere else, but in the roof of the Empire State, and you are here, then of course, in that case, yes, you have to include that contribution. Then let's delete this part. Excellent. Now, in advance, I wrote here by purpose the density of iceberg and density of salt water, and the reason is because I want to calculate now. The last time I explained the buoyant force over an iceberg, and I told you that most of the iceberg is below the water. And actually, I think I say it should be 60, 70, or 80% of the iceberg below the water, most likely. Let's see how much is it, because I don't really remember the number. But the idea is the iceberg is like this, and most of the iceberg is below the water. It's a huge, massive body. It's like a building crossing in front of a ship. The ship is like very small in front of the iceberg. So if you see it from the bottom, you will be more surprised. Then, of course, let's put the forces here. The forces here is mass of the iceberg, gravity, is the weight of the iceberg. The mass of the iceberg is density of the iceberg, volume of the iceberg, gravity. And of course, there is a buoyant force pushing up. There is a buoyant force pushing up. Buoyant force. And buoyant force is equal to what? Do you remember? Is the weight of the displaced fluid. So if you replace this portion by the water, the salty water, and calculate its weight, that's the buoyant force. That's quite amazing, no? So simple. Then let's put it. Buoyant force here is equal to density of salt water, volume immersed, gravity. In equilibrium, which is for obvious reasons is in equilibrium, the iceberg is not sinking, the iceberg is not flying to the space, it's not a rocket flying. There is an equilibrium condition. Then let's put here density of salt water, volume immersed, gravity has to be density of iceberg, volume of ice, gravity. Gravity and gravity cancel, so it means gravity doesn't influence in this calculation. So even in Mars, you will obtain the same result. It doesn't matter which planet you go, the result will be exactly the same, but the differences will come due to the density of the fluids in each planet, let's say. Assuming that you change, if we live someday in Mars, actually. There is a movie called Total Recall with Arnold Schwarzenegger, where it's very old movie, but I was a kid actually. Very kid, I must say. Very, very kid, and they portray the humans living in Mars. Of course, Mars has lower gravity. The ray of the clocks is different to the ray of the air. So if you are going to live in Mars, you have to take into account all these differences, a lot of physics in between. No? We can touch a little bit relativity later at the end of the course. So then, of course, the percentage of immersed iceberg will be density of salt water divided density of iceberg is equal, actually the opposite. Actually, I want to do the opposite. I want to calculate, this is iceberg, right? And this is volume immersed, because I put two I's, immersed. or I should put a different letter. No, I should put volume below. Let's put capital V or U under. Yeah, U under. U. Yeah, because people get confused. Then, of course, the fraction will be under divided volume of iceberg. This is the fraction of iceberg sank. And then this will be density of iceberg divided density of salt water. So density of iceberg is 0.9667. Density of salt water is 1.03. This is equal to what? Calculator, you can do it. Let me see if this calculator was also. 89%. So this is 0.89. So almost 90% of the iceberg is below the water. So what does it mean? That if you see the iceberg quite big and you are amazed about that, just think that most of 90% of that is below the water. That only represents 10%, let's say. You're only watching 10% of the body. Yeah. It's like equivalent, let's assume you have a kid 1 meter height. It will be like 10 centimeters of the kid outside the water. And the 90 centimeters inside. So it's more or less the proportion, no? So this is what we were talking about, the iceberg problem. Of course, I can ask you other fractions, like fraction, upper versus immersed, whatever. That's why I played with the equations last time. But in most of the cases, it's not necessary. Okay. And then let's summarize now the fluids, mechanical fluids. Now we review Buoyant force, we saw Pascal principle. We did two things. We did a hydrostatic, where you have columns of water. This classical problem of 3 holes here, 1, 2, 3, that the water escaped in the 3 cases, and there were different heights. So in general, this is approximately a hydrostatic because the level of the fluid doesn't change so much. In the long term, of course, it will change, but it's very slow change. But it's very slow. Hydrostatic is approximately correct here. In this case, no. In this case, so we calculated, remember that the pressure here, and pressure here. In general, the pressure grows with the depth, and that pressure, for example, pressure 3 will be the density of the fluid. What else? Gravity and the depth. And of course, if you have those, you have the density, you have the fluid, you have the density, gravity we know, and we have the height. And this is a special case of Bernoulli, if you analyze. Remember, Bernoulli, in Bernoulli you have pressure. You have to compare pressure 1, kinetic energy 1, which depends on velocity, and potential energy, which depends on the height. And you compare with this pressure 3. Well, let's put this 0 because this is outside the water. 0, 0. And this is 1 to 3. 3 velocity, 3 height, 3. Okay? When you do these comparisons, but in this case, there is no velocity, so there is no kinetic energy, and only there are different pressures and different heights. And it results in this formula. Just apply Bernoulli and you will see that you will obtain this formula exactly like that. And then, of course, the problems, I sent you already some problems solved, and the previous videos we explain everything. We don't have to calculate that. But remember that this, without any surprise, the velocity in each hole was rho square of, it's like the product of energy, you know? I think it's 2gh, I think. H is the depth. There is no surprise in that because Bernoulli is conservation of energy. I could ask you in the exam, parabolic. There's a parabolic motion here. I could ask you what's the distance reached by the water, for example, and then you have to apply from here to here conservation of energy, for example. This kind of problems can be done. And you will find that at the end of the day, you can apply conservation of energy from here to here, starting even from here to this point, and you will obtain. And finally, we did Bernoulli. And Bernoulli, I think the most interesting issue was the planes, the problem of the planes. I sent you the sample problem. Well, the sample problem is and we saw the problem of the plane here. We did in the class where you have the plane, the wings, passenger plane, or any plane. And of course, the plane has to fly at a huge speed, let's put 800 kilometers per hour. This is unrealistic. We know the weight of the plane. We can find in Google. There are different models, different weights, and we calculated the force which keep the plane flying. No? Then, of course, we apply Bernoulli in the upper side of the wing and at the lower side. Then the idea is that when the plane is flying, what should happen? The velocity of the wing in the upper side of the wing is much larger than the velocity below. And if you calculate pressure upper, the contribution of the kinetic part upper versus below, pressure lower, kinetic part lower, you will find a gradient of pressure pushing up. And we calculated it. And we proved it using the area of the wings. And so we proved that the gradient of pressure was enough for keeping the plane flying. We applied Bernoulli there. And of course, the difference in height between the upper and lower part of the wing is negligible. I mean, you really don't consider that part. Those problems are solved. I think, well, if you want, I can project them here, but I think you had those problems and I solved it the last class, so I don't have to repeat that part. So in summary, hydrostatic is a special case of Bernoulli, and Bernoulli is very useful in our current technology, as you can see. And even the aeolic energy, for example, for the aeolic energy, you have this kind of paddles, and the wing enter, the air flows. So the design of the paddles is similar to the design of the wings. So the air flows faster in one side than in the other. And then that creates a gradient of pressure. And then the paddle will start to rotate in the direction where the gradient, of course, in the direction where the net force is 10. For example, the pressure in this side is larger than the pressure in this side, obviously it will rotate in this direction. And if the pressure is larger here than here, what does it happen? In the energetic sense, the wind flows faster in this side or this side. It flows faster here in this side. And this is the aeolic energy of the engines you see. For example, you take the ferry from Macau to Hong Kong, you will see this kind of engine somewhere in the middle of the ocean. Actually, China is trying to use this kind of energy in the middle of the ocean. So I think it's quite useful. It's quite smart because it's free. In addition, it's just you just put the device and you get by free energy. As I told you, we have a lot of energy everywhere. We only don't know how to get it. Even here in this classroom, there is an infinite amount of energy. Well, infinite is an exaggeration, but a huge amount of energy everywhere. But the problem is how to extract it, how to make it useful. And this is where many laws come, thermodynamics, entropy, blah, blah, blah. All these things have to be combined for. So with this, we close the mechanical fluids. Let's put the key points. Hydrostatic, Bernoulli, Buoyant force, and with the Pascal principle. Yeah, I think we didn't do anything else. All this is the most useful things in your case, and even for those who do marine science, it's quite useful because if you go deep in the ocean, obviously the pressure will be huge. Those who design submarines, who design planes, also need to know this. Remember, if the plane is flying, the pressure is lower, blah blah. The cabin has to be pressurized. Don't open the doors. Don't open the emergency exits during flight. It's dangerous, quite dangerous. My concern is that when the flights become cheaper, more people got access to fly. But at the same time, many people with no offense, with no preparation, are inside the planes, not unconscious about the many issues, no? Unconscious about how the planes operate. And it had happened, these things in Korea, it happened that somebody feel hot, open the emergency exit, and it's serious that it happened. It sounds like a joke, but I mean, it's not a joke, it happened. And many other issues. In a submarine, some people were like, I can open the, I can see door, I mean, come on, man. If you open, it will catastrophic. What do you think will happen if you open a door of a submarine below the water? Exactly, a huge amount. Well, if it receives this sudden change of pressure, because it can even crash. No? With the planes, the same. A plane, the door opens, the plane, there is a chance that the plane can crash also. It depends how strong is the structure, but for sure, a wave of pressure, because that's another issue people don't study so much, that it requires some larger expertise. There is a wave propagated, no? Like the sound waves, no? Through the whole engine. So with this, I close the mechanical fluids. So I will start quantum mechanics in a moment.